Hi, I'm Bhargav and I'm a PhD student in IISc. For this course, I'll be taking weekly sessions where we would discuss and solve assignments from the previous offering of this course on NPTEL. Today we'll solve assignment from the week 0. So let me present my screen and we can start solving the problems. Okay, so the first problem is the following. Suppose a language A is decided by a 3-tape Turing machine. Which of the following is true? A. There is a single tape Turing machine that decides A. B. No single tape Turing machine can decide A. Or C. We cannot infer anything from the information given above. So the solution to this problem is that there exists a single tape Turing machine that can decide A. So now let's see why this is true. So suppose that we are given a 3-tape Turing machine M which decides the language A. What we will do is we will create a single tape Turing machine M prime which also decides A. To do this, we would divide the tape of M prime into 3 regions. The first region will contain cells numbered 1, 4, 7 and so on. That is cells of the form 3 n plus 1 for an integer n. The second region will contain cells of the form 2, 5, 8 and so on. That is cells of the form 3n plus 2 for an integer n. And the third region will contain cells 3, 6, 9 and so on. So cells of the form 3n for an integer n. And the reason we have divided M prime into 3 regions is that because M has 3 tapes, and what we will do is that we would use the ith region of the tape of M prime to store the symbols of the ith tape of M. So the ith region of M prime is exactly the ith tape of M. So the jth cell of the first tape of M would be stored in the 3j minus 1th cell of the tape of M prime. The jth cell of the second tape of M will be stored in the 3j minus 1 plus 2th cell of the tape of M prime, and the jth cell of the third tape of M will be stored in the 3j minus 1 plus 3th cell of the tape of M prime. So this is how we would store the tapes of M onto a single tape of M prime. However, M has 3 read-write heads which can move independently, while M prime has only 1 read-write head. So we somehow also need to store the positions of the 3 read-write heads of M on the tape of M prime. And to do this, we would slightly modify the alphabet of M to create a new alphabet for M prime. But over here by alphabet I mean the union of the tape alphabet as well as the input alphabet. So suppose that the alphabet set of M is sigma, then we would create a new set sigma prime, and this would be the alphabet set of M prime. Sigma prime would be the union of sigma and sigma hat, where sigma hat is a set defined as mentioned over here. So it is basically a set where for every symbol sigma in capital sigma, the symbol sigma hat is present. So basically we take every symbol from sigma, put a hat on it and put that symbol in sigma hat. So this is the tape, this is the alphabet set of M prime. Now I'll talk about how we would use this new alphabet set to store the read-write positions of the 3 read-write heads of M on the tape of M prime. So if the first read-write head of M is on the jth cell of the first tape and the symbol in the jth cell is sigma 1, then the symbol in the jth cell of the first region, that is the 3j minus 1 plus 1th cell, would be sigma 1 hat. This would signify that the read-write, so whenever we see that a symbol on the tape of M prime has a hat on it, it would signify that the corresponding read-write head of M is on that cell. Similarly, if the second read-write head of M is on the jth cell of the second tape and the symbol in that cell is sigma 2, then the symbol in the 3j minus 1 plus 2th cell will be sigma 2 hat. So the symbol in the jth cell of the second region is sigma 2 hat. Similarly, if the third read-write head is on the jth cell of the third tape and the symbol in it is sigma 3, then the symbol in 3j minus 1 plus 3th cell would be sigma 3 hat. That is, the symbol in the jth cell of the third region would be sigma 3 hat. So we have so far created three regions on the tape of M prime and used these regions to store the symbols on the tapes of M, and also we have also stored the positions of the read-write head of M on this tape of M prime. Now we would see how the state space of M prime would look like, and how using M prime we can simulate the execution of M. So to create the set of states Q prime of M prime from the set of states Q of M, we do the following. For every state Q of Q in capital Q, except the accepting and the rejecting states, and all symbols sigma 1, sigma 2 and sigma 3 in capital sigma, we add the states Q, Q comma sigma 1, Q comma sigma 1 comma sigma 2 and Q comma sigma 1 comma sigma 2 comma sigma 3 to Q prime. Now let's talk about how M prime would simulate a step of execution of M. Suppose that the current state of M is Q, then the current state of M prime would also be Q. Then what M prime would do is the following. Starting from the first cell, it would scan the entire tape to find a cell C1 in the first region of its tape containing a symbol from sigma hat. Let us suppose that this symbol is sigma 1 hat. Now what does this mean? This means that the read-write head of the first tape of M prime is on a cell which contains the symbol sigma 1, and once M prime finds such a symbol sigma 1 hat, it enters the state Q comma sigma 1 from its state Q. After it has done this, it again goes back to the first cell of the tape and scans the entire tape to find a cell C2 in its second region containing a symbol from sigma hat. Let's call this symbol sigma 2 hat. Once it finds such a symbol, it enters the state Q comma sigma 1 comma sigma 2. Again, starting from the first cell, it scans the entire tape to find a cell C3 in the third region containing a symbol from sigma hat. Let us suppose that this symbol is sigma 3 hat. Once it finds such a symbol, it enters the state Q comma sigma 1 comma sigma 2 comma sigma 3. Now let us understand what this state Q comma sigma 1 comma sigma 2 comma sigma 3 means. It means that the Turing machine M is in state Q and it has read symbols sigma 1, sigma 2 and sigma 3 from its first, second and third tapes respectively. So now using this state and the transition function of M, we can figure out what the next state of M would be. Okay, so then if M on reading symbol sigma 1, sigma 2, sigma 3 transitions from state Q to Q prime, what we would do is that we would also have the Turing machine M prime transition to the state Q prime. Now to complete this step of M prime also has to update the tape contents and the head positions. And to see how M prime would do this, we would use an example. So suppose that M updates the symbols sigma 1, sigma 2 and sigma 3 to sigma 1 prime, sigma 2 prime and sigma 3 prime, and moves the first read-write head one position to the left, the second read-write head one position to the right, and does not move the third read-write head at all. Then we'll see what M prime does to capture this operation of M. Then what M prime does is it writes sigma 1 prime in the C1th cell. It also, if the C1 plus 3th cell, that is the next cell after C1 in the first region of the tape of M prime, contains the symbol sigma 1 double prime, and it is replaced by sigma 1 double prime hat to signify that the first read-write head of M has moved one cell to the right. Oh, sorry, there is a typo over here. In the example over here, it should be that it moves the first read-write head one step to the right, the second read-write head one step to the left, and does not move the third read-write head at all. Now similarly, M prime writes sigma 2 prime in the C2th cell also, if the C2 minus 3th cell, that is the previous cell in the second region of the tape of M prime, contains sigma 2 double prime, then it is replaced by sigma 2 double prime hat to signify that the second read-write head of M has moved one cell to the left. Also, M prime writes sigma 3 prime hat in the Cth cell to signify that the third read-write head of M hasn't moved at all. And then after it has done this, M prime executes the next step of M in a similar manner. So we have just shown how M executes one step of M prime, and it can repeat this process to execute all the steps of M as well. Okay, and it continues to do this until it reaches either an accepting state or a rejecting state. If it reaches an accepting state, it accepts the string. If it reaches a rejecting state, it rejects the string. Okay, so it's clear that M prime accepts a string if and only if M accepts the string. And because of this reason, M prime also decides the language A. So we have created a single tape Turing machine that also decides the language A, and so the answer is that there is a single tape Turing machine that also decides A. So now let's move on to the second problem. Which of the following is not a part of a Turing machine? The options are states, stack, tapes, and heads. The answer to this is a stack. This is so because the Turing machine does have states, it does contain tapes, and it does contain read-write heads. However, it does not contain a stack. It's not a Turing machine that contains a stack, but it's a push-down automaton that contains a stack. Okay, so now let's move on to the third problem. The third problem is, which of the following constitutes a configuration of a Turing machine? The options are state, input alphabet, tape contents, head positions, and transition function. Over here we have to select all the options that constitute a configuration of a TM. So the answer to this problem is option A, state, option D, tape contents, and option E, head positions. This is so because a configuration of a Turing machine is a snapshot of the Turing machine at some point in time. So if I were to give you a snapshot of a Turing machine, that is, if I were to give you a configuration of a Turing machine, you should be able to continue the execution of the Turing machine starting from that point. And now to give you a snapshot of the Turing machine, I need to obviously give you the state, the tape contents, and the head positions. And so a configuration contains states, the current state, the tape contents, and the head positions. Now let's move on to the fourth problem. Consider a non-deterministic Turing machine N and a configuration C of N. We have just seen what a configuration is in the previous problem. Among the following options, select all the options that can possibly be the number of successor configurations of C. So what this question says is that suppose we are in a configuration C, and after N makes a transition, how many new configurations can it be in? The options are 0, 1, 2, 10, and 100. The answer to this problem is all of these, and this is because of the following reason. So starting in a state Q in capital Q and reading symbol sigma 1 to sigma k from its tapes, N can transition to any number of states in Q because it is a non-deterministic Turing machine. And every new state would be part of a distinct configuration because every configuration contains state, tape symbols, tape contents, and head positions. So different states would be part of different configurations. Because of this reason, N can be in any number of configurations. In particular, N can be in zero configuration. N can be in zero new configurations if M has reached the halting state. So for example, if N has reached an accepting state or a rejecting state. Now let's move on to the fifth problem. Consider a non-deterministic Turing machine N that takes as input a string X. Select all the possible options that lead to N accepting X. The options are all configuration paths lead to reject, exactly one configuration path leads to accept, more than one but not all computation paths lead to accept, and all computation paths lead to accept. The answers are exactly one computation path leads to accept, more than one but not all computation paths lead to accept, and all computation path leads to accept. This is so because a non-deterministic Turing machine n accepts a string if and only if there exists at least one computation path that leads to accept. And as you can see, in all the options except for the first one, there exists at least one computation path that leads to accept. So the answers are options B, C and D. Now let's move on to the sixth problem. Suppose a language B can be decided by a non-deterministic Turing machine n. Then which of the following is correct? Option A is there exists a deterministic Turing machine that decides B. Option B is that no deterministic Turing machine can decide B. And option C is it cannot be inferred from the given information. The answer to this problem is A, there exists a deterministic Turing machine which can decide B. And to see why this is the case, we would construct such a deterministic Turing machine. So suppose we are given a deterministic Turing machine n that accepts B, we would consider suppose we are given a non-deterministic Turing machine n that accepts P, we would consider a deterministic Turing machine M that accepts it. And to see this, let's see how using a deterministic Turing machine M we can quote unquote simulate the execution of n. So suppose that n from its current state sigma and current state q and reading tape symbol sigma from its tape transitions to q1 to qk comma sigma prime comma h, where h denotes whether the read write head has moved one cell to the right, one cell to the left, or not moved at all. Recall that from the first problem we can assume without loss of generality that n has only one tape. Okay, yeah, so over here we are just reading one symbol from its one tape. So if n does this, it transitions from this state to this, then what M will do is the following. It first transitions to the state q1 sigma prime comma h and explores the computational path that results from this transition. And once it has explored this path completely, if this path leads to accept, then leads to an accepting state, then M accepts the input string and halts. Otherwise, it backtracks to this state q comma sigma and transitions to the state q2 comma sigma prime comma h and again explores the resulting computational path. Again, if this computational path leads to an accepting state, it accepts and halts. Otherwise, it backtracks to q comma sigma, transitions to q3 comma sigma and repeats this process for all states in q3 to qk sequentially. And in this way, it's clear that M explores all the computational paths of n and halts and accepts if and only if some computational path of n leads it to an accepting state. Also, if no computational path of n leads to it to an accepting state, then M rejects the input string and halts. As x is in B, that is n accepts B, if n accepts x, if and only if there is a computational path of n that accepts x, it is clear from the way we have constructed M that M also accepts x if and only if x is in B. And because of this reason, M also decides a language B. So we have constructed a deterministic Turing machine that also decides B, and so there exists a deterministic Turing machine that decides B, and this is the answer. So now let's move on to the seventh problem. Suppose we have a multi-tape Turing machine and want to decide if the input string is a palindrome or not. Recall that a string is a palindrome if it reads the same in both directions, forward and reverse. So for example, the string BAB is a palindrome because its reverse is also BAB. However, a string BACB is not a palindrome because its reverse is BCAB, which is not the same as BACB. So suppose we want to decide whether an input string is a palindrome or not using a multi-tape deterministic Turing machine. The question is, what is the running complexity of the fastest algorithm that we can use to decide this? And in what follows, that is the following options, n is the length of the input string. So the options are O1, O log n, On, On log n, and On square. The answer to this is On. And to see this, first of all, notice that the answers cannot be O1 and O log n because at the very least, a Turing machine would have to read the string, which would itself take n time. Okay, So in the best case, the answer can be On. And now we'll show that there exists a multi-tape Turing machine which actually just takes order n time to decide whether a string is a palindrome or not. So suppose that the input string is x, then in order n time we can easily copy the reverse of x denoted by x to the r to the second tape. The way to do this is to go to the last cell of the first tape which contains x, and from that cell move to the left, and every time we encounter a new symbol we put it on the second tape. So in this way we can write the reverse of x on the second tape. So now the first tape is x, the second tape is xr. So all we need to do to check if the string is a palindrome or not is to compare these two strings and make sure that they are exactly the same. And we can do this by going over all symbols of x and x prime and checking if they are the same strings in order n time, because we just need to, there are n symbols and we need to just compare the symbols sequentially. And the total time taken is On plus On, which is just 2On, which is just On. So we can decide whether a string is a palindrome or not in order n time. Now let us move to the 8th and the last problem. And this problem asks us whether this statement is true or false. That is, if 3n square plus 7n plus 8 is equal to On cube or not. The answer to this problem is that it's true. And the reason is the following. Recall that a function f of n is equal to O of another function g of n if there exists an n0 in the set of natural numbers and a constant c greater than equal to 0, such that for all n greater than equals to n0, fn is less than or equals to c times gn. Now for this given function, notice that for any natural number 3n square, any natural number so for any natural number greater than or equals to 1, 3n square plus 7n plus 8 is less than or equals to 3n square plus 7n square plus 8n square, which is 18n square. Thus, if for any n greater than or equals to 18, 3n square plus 7n plus 8, which is less than or equal to 18n square, is less than or equal to n cube. And therefore, if we take n0 to be 18 and c to be 1, we see that f of n, that is 3n square plus 7n plus 8, is less than or equals to 1 times gn, which is n cube, and so f of n is order n cube. Here there is a typo, there should be order n cube. So that was all for this week. See you next week. Thank you.